Okay, so welcome to this third lecture in our linear algebra course. Today we'll be seeing an example of a set that is a vector space, and we'll actually prove that it is indeed a vector space. So let V be the set of all real numbers, of all positive real numbers. Of all positive real numbers. Okay, and you could also denote it as R plus if you took real analysis. And we define the addition operation as x plus y is mapped to xy. Okay, so this is really the multiplication of two real numbers, and the scalar multiplication is defined as alpha. I'll actually use the vector subscript just to understand that these are vectors we're dealing with, right? They don't necessarily have to be arrows with a length and a direction. A vector can really be any object that belongs to a vector space. Okay, and here instead we define scalar multiplication to be x to the power of alpha. And again, x and y are real numbers, right? They're positive real numbers. Okay, so I have to show that these VC operations satisfy the conditions for a vector space, which we saw in the first video. Okay, so let's take for every x, y, and z belonging to V, and for every, well, here we're really working over the positive real numbers. So the field is R plus. So for every alpha and beta belonging to R plus, then VS1, we have to prove that VS1 is satisfied. So that means that x plus y must belong to V. Okay, so how do we prove this? Well, note that x plus y is equal to x times y, right? And since x and y are positive real numbers, their product must also be a positive real number, right? That is how the field of positive real numbers works. And so we have that this must be greater than 0, and since x and y are both real numbers, x times y must also belong to R. So this implies that x, y does indeed belong to V because it is a positive real number. Okay, so I've shown that since x plus y is equal to x times y, there is closure under addition. Okay, now we have to do the same for scalar multiplication. So if we take alpha, right, multiply it by x, then this must belong to V. How do we prove this? Well, again, we defined the scalar multiplication to be just x to the power of alpha, right? But since x is positive and a real number, x to the power of alpha must also be a positive real number. And so we just prove that this is a real number and that it must be positive because x is positive. So x to the power of alpha must belong to V. And these are pretty straightforward. Now VS3 has to do with commutativity. So we have to prove that addition is commutative. So if you take x plus y, this is equal to x times y, right? Multiplication of real numbers. But because the positive real numbers also have commutativity, right? It is an abelian field or a commutative field. We can write this as y times x. Okay, and now using again our definition of addition, this is equal to y plus x. And here we've shown that addition is commutative. Now VS4 instead is associativity. So if we take x plus y and then add z, that is equal to xy plus z, and again using our addition, we get that this is equal to x times y times z, and using the associativity of multiplication in the real numbers, this is equal to x times y times z, and this is equal to x times y plus z, right? We used here the addition, and again we'll use the addition again and write this as x plus y plus z, and there we go. We have just proven the associativity. Now VS5 instead is distributivity. So if we take alpha dot x plus y, right, what is this equal to? This is equal to alpha times xy, and we defined scalar multiplication to be the power or the exponentiation. So this is equal to xy to the power of alpha, and if we want to go further, we can just write x to the alpha times y to the alpha. Okay, now we have to prove that this is equal to alpha dot x plus alpha dot y. Okay, this is equal to, well, alpha dot x is equal to x to the power of alpha, and alpha dot y is equal to y to the power of alpha. So we have this addition, and again, addition means just multiplying the two real numbers. So this is just x to the alpha times y to the alpha, which is equal to alpha times x plus y. Great. Now let's just do the same for VS6. So we're halfway through really. So VS6 states that alpha plus beta times x, well, what is this equal to? This is equal to x to the power of alpha plus beta, right? We're using this as exponent, and we can use the properties of the real numbers to split this into these two, into this product. And now let's see if this is truly equal to alpha x plus beta x. Well, alpha times x is equal to x to the power of alpha, right? And beta times x is equal to x to the power of beta, right? And since we're adding these two, it's the same as multiplying them over the real numbers. So this is equal to x to the alpha times x to the beta, which is equal to alpha plus beta times x. Okay, so we have this distributivity proven. Let's now prove the associativity of multiplication, of scalar multiplication. So if we have alpha times beta times x, right, this is equal to alpha times x to the power of beta, and this is equal to x to the power of beta to the power of alpha. And using the properties of the real numbers, we can write this as x to the power of alpha beta, right? Just actually, if we wanted to be very precise, this is equal to x to the power of beta times alpha, and using the commutativity of the positive real numbers, we can write this as x to the power of alpha times beta. Okay, now let's prove that this is equal to alpha times beta times x. Okay, so again, using the definition of our scalar multiplication, this is equal to x to the power of alpha times beta, which is exactly what we got here. So scalar multiplication here is also associative. Okay, we need a new page now. Okay, so now VS8, 3 more to go. VS8, we have to show that there is the zero vector. Okay, so what could be a possible zero vector? Obviously, just the real number oh sorry, yeah, the real number 1, right? Why? Because if you use 1, right, and I'll put the bar underneath, right, obviously 1 belongs to the vector space V, right? It is a positive real number. And if we take the addition, right, so we take any vector x and add 1, right, this is the same as doing the multiplication of the two. So what is x times 1? Well, it's just equal to x. That is how the real numbers work. And that is precisely the definition of the zero vector. So here 1 is our zero vector of the vector space. Okay, VS9, we have to show that there is an additive inverse. And here what we can use is really we want a number such that its product is equal to 1, right? 1 is a zero vector. So if we take x, right, and we add it with y, right, this is equal to x times y, and we want this to be equal to the zero vector of the vector space V, which we said was 1. Okay? And since neither of the two can be equal to 0, because these are positive real numbers, we can simply say that the additive inverse y is 1 over x. Okay? And this exists for every vector x, and it is also and it also belongs to the vector field V, right? Because x is a positive real number, 1 over a positive real number is a positive real number. Okay, so we have that the additive inverse is 1 over x. Finally, VS10. VS10, we have to show that 1 times x is equal to x. Well, what is 1 times x? It is equal to x to the power of 1, right? And what is a real number to the power of 1? It's just that real number. Okay, so obviously all the conditions VS1 through VS10 are met, and consequently V is indeed a vector space.